All right, so in this video, we're going to be proving that convergent sequences are bounded. In this case, we have a sequence AN, where each n is a natural number. We have that is a convergent sequence, and we want to show that it is bounded. So, to start off, we're just going to kind of reiterate some things and say let AN and an n be a sequence converging to some value, which we will call L, and L is a real number. So this is just saying that we have a convergent sequence and it converges to some value, L, which is a real number. Now, it follows that since the sequence is convergent, for all epsilon greater than 0, there exists a large n in the natural numbers such that once we get past this large n, once our terms, our terms are indexed past this large n or at it, we have that the difference between an and the supposed limit is less than epsilon. So this is just the definition of a sequence converging to some value L, but we could say that notice the set of the terms in the sequence an for each n is a natural number, but n is less than this large n is finite, because we're going up to some large n. All the terms before that are bounded above by this large n, and we know that the natural numbers are bounded below because they start at 1. So that means that this is bounded, because it is finite. We have a finite amount of terms up to this large n. However, we still have to consider all the terms at this large n and past it. But before we move on to that, let's say let m, lowercase m, and capital M be lower and upper bounds respectively of the mentioned set. So we're saying let small m be a lower bound for the set, and let this large m be an upper bound for the set. Now I'm going to erase this just to clear up a bit of space. All right, so what I have written here is just saying what I had at the bottom before I erase it, where lowercase m is a lower bound for this set, where we have the n that are less than this large n, and capital M is an upper bound for this set. Now, let epsilon be greater than 0, and recall that for all n greater than or equal to this large n, we have a n minus L, absolute value is less than epsilon. And this just follows from the definition of a convergent sequence. Now we can get rid of the absolute value, and we have that an minus L without the absolute value is less than epsilon, but it's also greater than negative epsilon. And now we can add this L to all of these sides of the inequality, and we get negative epsilon plus L is less than an, which is less than epsilon plus L. So now we have that this is true for all n greater than or equal to n. So an for all n greater than or equal to n is bounded above by epsilon plus L and negative epsilon plus L. So I'm going to erase that and rewrite some things here. just going to scribble in what we just talked about and say, notice an, you set an where n is greater than or equal to n, oops, an where each n is a natural number, and n is greater than or equal to n, is bounded above by epsilon plus L and bounded below by negative epsilon plus L. Now, consider the following, where we take the minimum of this small m and negative epsilon plus L, and also consider the maximum of the large m and epsilon plus L. So we're taking the maximum of both of the upper bounds for the separate sets that we had, and the minimum of both of the lower bounds that we had. So if we take the smallest lower bound of both of the sets, it should bound both sets below. And same principle follows for the maximum for the upper bound. So now, consider the union of the two sets that we have talked about, which are an, where n is less than this large n, union with the set an, where each n is a natural number, and n is greater than or equal to large n. This equals the set an, where each n is an n. So the whole set is put back together. It is bounded above by the minimum of lowercase m and negative epsilon plus L, and is also bounded below by the, it is bounded below by the minimum of lowercase m and negative epsilon plus L, and it is bounded above by the maximum of the large m and epsilon plus L. So we have shown that it is bounded, that the sequence an, where n is an n, that is a convergent sequence, is bounded. And this completes our proof.